Today we start one important topics related to non-linear space. We start from basic definition. Okay, we write here definition and we start from this definition. Let Y be a subspace of a noun space. X noun over K. Then first one, here Y is said to be closed. Y is said to be closed if Y contains all its limit points. If Y contains all its limit points. Or yn in Y with yn converges to Y belongs to X. This implies that Y belongs to this Y. Okay. And number 2, Y is said to be complete. Y is said to be complete if every consequence in Y converges in Y. Okay, now we write here, we write some proposition. Okay, if Y be a subspace of a norm space X norm, then Y closure be a subspace. Okay, and also this one some proposition. Okay, that means Y be a, we write this one, Y be a subspace of a norm space X norm, then Y closure be a subspace. Okay, we erase this portion now and going to be discussion about one theorem about that. Let Y be a complete subspace of a norm space X, of a norm space X, then y be closed, then y be closed. We write here properly proof. Let yn be a sequence in y, yn be a sequence in y, such that yn tending to y, such that yn tending to y belongs to x. Okay, then we have to prove y be closed. That means y belongs to, if y belongs to y, then this one is done. So what we do here, since here we write the, that means one assumes, that means one necessary conditions are given this one. Since y be complete, okay, it follows that yn is convergent in y, yn is convergent in y. Therefore y belongs to this one. Thus we conclude that y be closed. Okay, so now we're also going to one important theorem. Okay, let y be a subspace of a Banach space A. Then the following are equivalent. First one, y be complete. Second one, y be closed. Let y be a subspace of a Banach space X, then the following are equivalent. Y be complete and y be closed. Okay, this one are equivalent. We have to prove those ones. Too easily we prove it. Now we erase that portion and going to prove of that theorem. Okay, suppose that y be complete. Let yn be a Cauchy sequence in y. such that yn converges to y belongs to x. Now note that yn converges to y and yn converges to y, that means yn convergent, so yn convergent, and this implies yn cos. Okay, since y be complete, it follows that yn convergent in y. Therefore y belongs to this y. Okay, hence we conclude that y be closed, not a problem at all. Okay, y be complete, that means every Cauchy sequence is convergent, we have to prove, and obviously we take a Cauchy sequence in y, and obviously this one convergent in x, but we see that yn convergent, so yn Cauchy, and since y be complete, because y be a subspace of a Banach space x, so x complete, that means y complete, it follows that sorry here, that means if y complete, this one is needed. Okay, that means we write some statement is, oh sorry, they needed, because a implies b, over here y complete is given. Okay, oh sorry, y complete is given, so y complete, hence yn convergent in y, that means x Banach space and y complete is given. Always not every subspace is complete. Okay, so here y closed too easily, this one is proved. Okay, now we're going to further discussion of that. That means we assume that y closed and we prove y complete. Okay, so we suppose that y be closed. Okay, for this let yn be a Cauchy sequence in y, yn be a Cauchy sequence in y. Okay, Now since yn is Cauchy in y, and then obviously yn is Cauchy in x, okay, because y is subspace, this one is whole. So yn be Cauchy in x. Okay, so what happened? We erase our portion now and going to further discussion of that. Yn be a Cauchy sequence in x, okay. Then yn converges to y in belongs to x. This implies yn converges to y belongs to x. Okay. Let yn converge to y belongs to x, okay, and y be closed, and y be closed will also obviously considered. Then what happened? Then the Cauchy sequence in y converges to, that means then y belongs to this y. Now Cauchy sequence yn in y converges to y, y belongs to this one, okay. So y be complete. So y be, that means closed implies y be complete, okay. We not write this one, that means closed implies complete. This one is proved, okay. So we also done it. Another, that means another theorem we also discuss later, but obviously this time what we prove, we just prove definition, we just prove one theorem, which is y complete implies y closed when y be a subspace of a Banach space x, okay. And obviously this one important theorem, and obviously another one we also prove y be complete then y closed, complete subspace closed, same thing. And obviously we prove another one, that means prove not, just write this statement, that means y closure be a subspace of a norm space x. And obviously we say write this definition of closed, okay, closed, then some space be closed when the y contains all limit points, okay. So today we stop here.